DC motor and AC generator. A direct current motor uses the motor effect to exert a force on a current carrying wire. The motor is designed to cause a coil of wire to rotate. When electric current passes through a coil in a magnetic field, the magnetic force produces a torque which turns the DC motor. When the coil is rotated a half turn, the commutator will reverse the current in the coil. This means that the direction of the force on the coil will still cause the left side to be pushed upwards while the right side is pushed downwards. As the force remains in the same direction, the coil continues to spin, producing a turning moment which can be used to do work. What would happen if the battery is turned in the opposite direction? Of course, it would turn the other way. Because remember, the turn is dependent on the direction of the flow of current. Okay? So electrical motors are used in a wide range of devices. They're used in fans, cars, toy planes, etc. A DC motor transfers electrical energy into kinetic energy. Using the motor effect, it uses a current carrying coil of wire which is made to rotate inside a magnetic field. Alternating current generators use induction to produce a current in a wire by rotating a coil inside a magnetic field. They are similar to direct current motors physically. However, kinetic energy is transformed into electrical energy. Here we have an alternating generator, a loop of copper wire. So a wire loop is rotated between the poles of a magnet, inducing a current in the wire. The current is transmitted through slip rings and brushes. During a full rotation, the coil will produce an alternating electromotive force as shown in the figure below. When the coil is horizontal, it will cut field lines at a high rate and a large EMF is produced. When the coil is vertical, it does not cut field lines and so no EMF is produced. It passes straight through the wire. So when it's horizontal, you see that it's blocking the magnetic field. So these are the magnetic fields right here. Fleming's right-hand rule uses the same idea. You have the thumb for motion, the magnetic field is the second finger, and the direction of current is the third finger, right? So here we have that. So we have the motion in your thumb, the magnetic field in your finger, your little finger here, and the current is in your third finger. It's the same idea, right? Just one is used for motors and one is used for generators, which is the right hand. So if the coil in an AC generator is rotated faster, a larger EMF is produced. It will also increase the frequency of the AC supply. Some power stations generators are spun 50 times each second, producing a frequency of 50 Hertz. Remember, frequency is per second, right? So that's the amount of cycles done in a second. While others are spun 60 times each, producing 60 Hertz. So Fleming's left-hand rule, Fleming's right-hand rule. Let's look at it. Let's compare. Fleming's left-hand rule is used when dealing with motors, whereas Fleming's right-hand rule is used when dealing with generators or dynamos. In problems for Fleming's left-hand rule, the direction of current and magnetic fields are given. In problems for Fleming's right-hand rule, the direction of force and magnetic fields are given. In Fleming's left-hand rule, force of motion of the wire is to be derived. In the right-hand rule, the direction of induced current in the wire is to be derived. So please, please, please take this down. And this is very good information for you. Now we're moving on to the final topic, which is transformers. You made it to the end. Whether you understood or not, it's going to come. Watch the videos over again. Not only that, I am going to bring questions. Visit the questions and you'll be getting better and better all the time. So transformers, we are transformers, right? So the voltage of an alternating current can be changed with a device called a transformer. The transformer also changes the size of the current. When electrical energy is transmitted over long distances, it is best to do so at high voltage. Remember, voltage is the flow. That's the flow, right? So when you increase, it's like turning on a pipe. When you turn on the pipe, a small trickle, a little bit of water come out. Turn up the voltage or turn up the pipe, a lot of water come out. You turn up the voltage, a lot of electricity come out, right? And low current, right? So high voltage, low current. Why? Because we need the current to travel efficiently to homes, right? We also, well, I'm talking on the grand scale of things. A low current because if you have a high voltage, a lot of electrons entering some type of body. A low current will guarantee maybe life, but more than likely not. But it's just a safer alternative to doing high current, high voltage. I think that would also cause a fire. That might very well cause a fire. Now, a transformer consists of two coils of wire wrapped around opposite ends or arms of a laminated iron core as shown below. The primary coils are the input coils and the secondary coils are the output coils. You can see it right there. So you have the primary is usually on the left hand side. Well, it's on the left hand side and the secondary is on the right hand side, right? So it's always like that. Primary on the left, secondary on the right. A transformer cannot work with direct current because it works by using changes in magnetic fields. Transformer equation is such that the voltage in the secondary coil is divided by the voltage in the primary coil equal to the number of turns in the secondary coil times the number of turns in the divided by the turns in the number of turns in the primary coil equal to the current in the primary coil divided by the current in the secondary coil. Please note, secondary for voltage and secondary for number of turns is in the numerator here, and current in the primary is put here. Primary for the current. If you want to flip, you could actually flip. You could put Vp over Vs equal to Np over Ns equal to Is over Ip. You could flip them. Transformers. So we give transformers names like step up or step down. Here's an example. You have a step up transformer here because you're going from less turns to more turns. So you're definitely stepping up the turns. And step down transformers, you're going from more turns to less turns. Good. Here we have 25 kilovolts, that's 25,000 volts from a power station going in a step up transformer. So definitely the voltage is going to be higher, current lower. Traveling through the power lines and then eventually coming into your homes, they have to use step down transformers. Those substations you see outside your homes, they step down the voltage and allows the current to enter into your homes. And there it is. That's the end. So thanks for following along with me, and look out for the questions that will come on static and current electricity, magnetism and transformers. It was good. Bye now.